Alright, in this video we're going to look at section 1.20 called Picture This. So you're going to need your e-text again, and the pages that this is on, let's see if I can get this to work. We got page 114 through 116. Alright, so let's get started. So I want you to take a second and just read through this scenario here. Go ahead and pause the video while you do that. Alright, so when you have so much information like this, it's really good to read through it more than one time. So that was just kind of a first read through to get an idea about what this problem's about. And we're going to go back and read through it again. And we're going to plot this information on a graph. So on this graph right here, we've got time on the x-axis, which sometimes it's not x, like time in minutes might be a different variable, like t or m. So we call this the horizontal axis. Okay, and the variable that goes down here is called the independent variable. So time is independent. And here we have the vertical axis. And on our vertical axis we have speed. So the dependent variable in this case is speed. Okay, and the independent variable here is time. So as time changes, the speed's going to change based on the information that we have here. So the speed is dependent upon what time it is. Time's going to move along independent of whatever, and the speed is dependent upon the time. So that kind of helps to rephrase it that way to know what's dependent and independent. All right, so let's just start off with the first part together, and then I'll probably have you guys go through, see if you can do the next part. So on the axis below, draw a graph that you think is consistent with the following scenario. You merge onto the interstate at the start of a drive. Okay, so now we're just going to take first piece of information. It takes you 2 minutes to get to your cruising speed of 70 miles per hour. All right, so at time 0, we were going 0 miles per hour. So I'm going to put a dot right here. Okay, at time 0, I'm going 0 miles per hour. After 2 minutes, it takes me 2 minutes to get to my cruising speed of 70. So after 2 minutes, I'm at a cruising speed of 70. So this dot right here represents after 2 minutes, I'm at a cruising speed of 70. So I'm going to assume that I'm like increasing my speed here. Now it doesn't give me a lot of information about what's happening between 0 and 2. Did I like speed up really fast? So I'm just going to assume this is like kind of a straight line. So I'm going to draw a straight line there. Okay, that's my straight line. It's off just a little bit here, but it's supposed to be going from 0, 0 to 270. All right, then you go to the next piece of information, and you plot whatever that piece of information is. So the next piece of information says you stay at 70 miles an hour for another 8 minutes until you see a police car. All right, can you plot that on the graph? Go ahead and pause it and see if you could plot that on the graph. All right, so hopefully you plotted that you're going to stay at 70 for another 8 minutes. So I was at 2 minutes, so another 8 minutes would take me to 10 minutes. So from 2 minutes to 10 minutes, I'm going to stay at 70 miles per hour. So my graph's going to look like this. All right, now we go to the next piece of information. Let me get rid of these guys here. Okay, so next piece of information. You quickly slow down to the posted speed limit of 65 and stay there for about 10 minutes until the police car finally exits. So here at 10 minutes, I'm going to quickly slow down to 65. It doesn't really tell me how quickly, so I'll just do it pretty fast. Let's say, you know, just like coming straight down to 65 like that as fast as I can. And I'm going to stay there for about 10 minutes. So I was at 10 minutes already, so if I add another 10 minutes, that would take me to 20 minutes, where I'm going to stay at 65. All right, go ahead and pause the video and see if you can finish the rest of this graph. All right, so let's go to the next piece of information, see how you did. Then you quickly accelerate to 80 miles per hour and remain at that speed for about 5 minutes until you see the exit. So from here, I'm going to go to 80 miles per hour quickly. So I'll go a little bit past 20 minutes because I can't do it, instantaneously. It's got to be a little bit of time passing. And I'm going to stay there for about 5 minutes. So I'll go to 25 minutes. I was at 20 minutes. You could go to 26 if you think you spent a minute accelerating up to 80. You could go a little bit closer to 26. There's no perfect answer here. All right, so the next thing it says is you exit into a residential area with a speed limit of 30, which you obey for the remainder of your 30-minute drive. All right, so from here we're going to go down to 30 miles per hour. Let's plot it right there, see if I can draw that line. And then I'm going to remain at 30 miles per hour for the rest of my drive, 30-minute drive. So actually, since it's only a 30-minute drive, I should just go out here to 30 minutes. That's going to be the end, and it stops right there for my 30-minute drive. So this information tells us our speed over the 30-minute drive. And that's a picture. I mean, isn't that picture so much nicer than all this information? This really gives me a good idea. Like if I said, hey, when were you going the fastest? Did I miss my 80? Gosh darn it, I did. I missed my 80. Let me fix it. This was supposed to go up to 80. Did you guys catch that? These little lines are hard to see sometimes. He was going 80 miles per hour up to here. There we go. Is that better? Okay, so if I gave you all these words and said, when will you go in the fastest, you'd have to read through it and you could probably figure it out. But if I give you this picture and say, when was he going the fastest and how fast was he going, it's so obvious right here. This picture is so much easier to interpret that, between the minutes of about 21 minutes and 25 minutes into his drive, he was going 80 miles per hour. So we're going to talk about graphing and plotting information and interpreting information on a graph. So there are lots of real-world examples, many, that we can visualize with a graph. So let's start here. We have seen examples of linear and exponential change. That was from last time. Do you remember linear? Let's review that real quick. So a linear graph is going to make a graph of a line, but you get that by adding or subtracting the same amount each time. Each x value you add or subtract something, and then exponential, we're multiplying by something, like a multiplier or increasing by a certain percent. And those graphs kind of look like that. That's exponential growth, and a graph like this would look like exponential decay. This would look like linear growth, and this would look like linear decay. All right, it's important to understand not every situation is linear or exponential. The scenarios that follow will give you some examples of other situations and the graphs that illustrate them. Match each description to the graph that you think best illustrates. Identify the independent and dependent variable in each case. All right, so let's go through first and do the independent and dependent variable, and then the graph that we're matching it to is number 7, which is over here. Is all these graphs. Maybe we'll do, you guys can see them both on the same page, so that shouldn't be too hard to just look over to the other page. I'll just flip between these slides here. So you save the same amount of money each month in an account until you reach your goal. Then you leave it at that balance. So we want to figure out what is the independent variable here and what is the dependent variable. So I'm going to use I for independent variable and D for dependent. So think about what this graph would look like. You're not asked to graph it, but if you did graph it, what information would go here and what information would go here? All right, you save the same amount of money each month in your account. So this is going to be time, right? This is how much time is passing, and then this would be how much money you have. And if you save the same amount each month, it's going to look like this. You're adding the same amount each month. So our independent variable is time, and our dependent variable is dollars or money or how much money is in your account. Okay, let's go see if we can find a graph that we think looks like that from this over here. Well, we know we're adding the same amount each time, so it should look linear. This is the only one that sort of looks linear. It looks then, what's happening here? Right? He's not saving money anymore. He's just saving it for a while, and then he stops. So this is going to be F. So this is going to be number 2. I'll just mark it there so when we're doing the rest of them. So this is graph F. All right, if you want to, you can pause it and go through these yourself and see how you can do and match these up with all the graphs and get your independent and dependent variable. Then start the video when you're ready. Okay, so number 3, if we're thinking about average monthly temperature in a given location, this is going to be time again, because we're in some location and we're going to have like the days down here maybe, and then the temperature here. So let's say it gets hotter and then it gets colder or something like that, right? If it's months, say this is January, February, March, all the way to December. And so the temperature's cold in January and then it warms up, at least where we are, and then it gets colder in December, something like that. So the dependent variable is temperature. And if we look at our graphs, it gets warmer and then it gets colder. It's going to be something like this. So I think A, that's going to be problem 3. Now this would be saying the temperature just keeps getting warmer and warmer and warmer as the months go by. That's not what's going to happen, right? Now you could make an argument for E. You could say 3. I would accept this answer as well. The temperatures get warmer and then they get colder. You know, where we are, it's more kind of like this. It gets colder. It's not 0. Maybe this graph's a little misleading if this is supposed to be 0. It's not that cold here, but we're just looking at general shape, right? Okay, let's look at the next one. A population of bacteria doubles every hour. So again, if I'm thinking about the graph of this is going to be my time, and this is going to be my number of bacteria. So independent variable is time. Dependent variable is the number of bacteria. All right, what's this going to look like? Well, if I have some bacteria, and then if that doubles, and that doubles, and that doubles, that's that exponential growth. Right? You're multiplying by 2. So that's exponential growth. That should be something that looks like C, exponential growth. I'm going to say that's number 4. Number 5, the height of a ball each second after it's shot from a catapult. Each second. So again, we're looking at time. That's your seconds. And then the height of the ball. So here is going to be the height of the ball, measured in feet or meters or whatever. So my independent variable is time. Now I want you to notice something on a lot of these examples. Independent variable time, independent variable time, independent variable time, independent variable time. If time is involved, it's almost always the independent variable, because time passes, and then, you know, the height of the ball is dependent upon how much time has passed. The number of bacteria is dependent upon how much time has passed. So this is the dependent variable is going to be the height of the ball in feet or whatever they tell us. They don't tell us in this one. So what's that going to look like? All right, if I shoot a ball from a catapult or, you know, some kind of a launcher like a big slingshot, the ball's going to go up, and then what's going to happen? It's going to go down. That's it. It's going to go up and it's going to go down, and when it hits the ground here, means it would hit the ground, you're done. The ball's done moving. So that is definitely this graph as well. That is definitely that one. This would be saying the ball goes up in the air and then just stays up in the air, right? That's not it. This would be saying the ball goes up in the air and then comes down and then goes back up. That's not it, right? Okay. The number of days needed to build a bridge compared to the number of workers. Oh, interesting. Okay. So number of days needed, that's going to be, let's see. That's going to be one of our variables. And then the number of workers is going to be another one of our variables. So now, let's think about this one for dependent and independent. Which one of these is dependent on the other? Okay, let's read it both ways. Is the number of days dependent on the number of workers? Is the number of days needed to build a bridge dependent on the number of workers? or is the number of workers dependent on the number of days? Right? So let's think about that. And this one's a little bit tricky because really you could make an argument for either way. You know, you could say, I have so many workers. That's all I've got. I've got a certain number of workers, and then however many workers I have, the number of days it's going to take is dependent upon how many workers I could find. You could also say, you know what? I've only got so many days to build this bridge. And the number of workers I need is dependent upon how many days I need to have to get this job done. So honestly, you could make an argument for graphing this either way, and that's why it's important to label your axis however you do it. So if you're doing it, you know, this way, number of days and workers, that's fine. Just make sure to label your axis. If you want to do it the other way, that's fine too. Okay, so let's look at this graph and see what we have left. Now, depending on what we choose for our independent and dependent variable, that's going to change how the graph looks. These guys, your book did it by doing the independent as the number of workers as far as the graph, and the dependent as the number of days. So let's change this and then think about what the graph would look like. Number of workers, number of days. Okay, so if I have more workers, is it going to take more days or less days? Like, does that make sense? So let's say I have a certain number of workers and it takes a certain number of days, whatever that is. Okay? You know, you just make it up. Let's say I have 10 workers, and if I have 10 workers, it takes me 5 days. Great. What if I have more workers? Is that going to take less days or more days? It should take less days, right? If you have more workers, it should take less days because you can get it done faster. More workers, less days. If I have less than 10 workers, it should take more days. So we should get this kind of a shape, like that. And that looks like D right here. So I'm going to say this is my workers. Was that number 6? Okay. And then the last one we have is actually number 7 right here. The number of students on a college campus who contract a highly contagious flu. This example is a little too timely, isn't it? I mean, this book is old, but so in this example, we have time, and then we have the number of students with the flu, the number that have the flu. And hopefully it levels off. That's what you're hoping for, and then goes down. But you could even make an argument for this one. It could go up and then come down. It's not going to start high, right? It has to start low. Unfortunately, this is what we're seeing right now. Every day I go to Google and I type in Spokane COVID, and then I come down to this first result here from srhd.org. I click on that, and it gives us some information about what's happening. It takes a second to load here. Alright, so here we have the number of cases per day. And you can see back here, this is when they shut the schools down. But this is what's happening right now. I was so excited right here. I was like, oh, we did it. We got it. And then people started going out and not being careful, and now we have days, you know, between 50 and 100 new cases every day. And they were shutting down the school when we had 20 cases a day. Alright, so here's what this data looks like now. This is what's happening. What does that look like to you guys? The cumulative COVID cases, that looks exponential to me. That does not look like this, right? We're like still in this part. We're like this part right here. We haven't quite figured out what we need to do to start leveling this off, which is wearing masks and being diligent about social distancing and mask wearing. We haven't figured it out yet, so I'm a little discouraged about that. But this is what's happening. That's the data. That's the trend. And that's what I look at when I make my decisions. What's the trend? What's happening? And we're still in the exponential growth phase here. We have not started to come down yet. So I encourage you guys to look at this every day and think about what's happening and the trend that's happening here. Alrighty, moving along. Statisticians often look at scatter plots to try to find a general pattern, kind of like what we were just looking at with the COVID cases, that the data points seem to follow. Even if it's not a perfect fit, for each of the following scatter plots, sketch a smooth curve through the points to indicate the model you think the data points seem to follow. You may choose a line, an exponential curve, or some other shape. So these are our choices: linear, exponential, or some other shape. The line or curve should look like it passes through the center of the cloud of points. It doesn't need to go through each point on the graph. All right, so here's an example where we have our independent variable, the number of times Facebook is checked per day. And the dependent variable is the time spent preparing for college classes. Okay, so what are we trying to say? What is this graph trying to say here? It's saying the more times a person checks Facebook, the less time that they spend prepping for their college class. In other words, they're getting distracted, right? So what does this look like to you guys? Does it look linear, exponential? Like generally what's happening? Can you see how it's generally a line here? So this is called a scatter plot, oops, where you gather information and you plot it. And it looks kind of scattered around. But it has a general trend. And that general trend is the more times you spend checking Facebook, the less time you spend preparing for class. So we could model that by inserting some line. I'll try to do the best I can making a straight line. I could put a ruler in here, but that's not bad. Something like that. Okay, that's the general line. I'm going to say this is following linear decay. Right? It means it's getting smaller in a constant manner, a linear manner. All right, there's 3 more of these graphs here. Why don't you guys pause the video and see what you think. Draw a graph in there you think fits. All right, so this next example we have experience. Remember, this is an independent variable, how much experience you have on the job. And then your salary is dependent on your experience, and that's true for many jobs. So we can see here, as the experience gets bigger, so does the salary. This looks kind of linear to me. It's a little bit of a shape like that, but I would say generally it kind of looks like a line. I would call this linear growth. And again, remember, this is not perfect. So you might want to argue it looks exponential. It might be barely exponential. Like if you were trying to do exponential, it might look something like, and then try to argue it does that. But I'm going to say this green graph is closer to the points than this red one. Maybe you could try to draw your red one a little bit closer to the points, but if you draw it closer to the points, it doesn't really do that exponential curve, you know, it goes away from that. So I don't think it's exponential. All right, this one goes up and then it comes down. The selling price and the revenue. So if I price it too low, I don't make enough money. If I price it too high, people don't buy it and I don't make money. There's some sweet spot in the middle there. So this kind of looks like it goes up generally and then it kind of comes down. So that's not linear and it's not exponential. It's some other kind of curve. We could call it upside down U shape. Upside down. I think your book just calls it U shape. It does have a mathematical name, which is called a parabola or a quadratic equation. And you'll do quadratic equations in Math 88. We're not going to worry about them in 87. So we can just call them U-shape. All right, so the last one, we have the year and the population. So the population is dependent upon the year. Starts off super, super, super low and then shoots up like that. Do you recognize that? This graph is classic exponential growth. Classic. I was actually watching the data from Wuhan back in February, and before it even got to other countries, the COVID got to other countries, and it was just following this exact pattern, and I was like, oh no, that's bad. that is not good, because this kind of exponential growth can just explode out of control, which is exactly what we've seen. So here we have exponential growth. All right, guys, this stuff is super, super important, being able to look at graphs, interpret graphs, plot graphs, think about independent and dependent variables, plot information that's not linear exponential, just so hopefully this makes sense, and if you have any questions, let me know.